Okay, we were talking about the different dimensions. We've covered the first algorithmic details, and now we're going to continue on embedded concepts. Okay, embedded concepts. Well, yes, there is the algorithmic part and there is the embedded part. They seem distinct of each other, although they are, quite strongly correlated. In the end, there comes the question, which embedded system and why, instead of how this algorithms works. So the main significance of this dimension of systems engineering for deep learning is to guide you guys, the designer, the researcher, the engineer, which embedded system and why it is. And in this dimension, we have many metrics and what we can call sub-dimensions. There are many dimensions inside this dimension. So for different embedded environments, these are the attributes that we can define. We call them in general computational attributes. Computational power, power efficiency, memory efficiency, stability, coder friendliness, and etc. In order to do proper systems engineering for an embedded system, first an engineer, a designer should understand these concepts, in my opinion. So we continue with those concepts, guys. We continue with computational attributes. The main purpose of an embedded system is to compute. There is no doubt about it. Embedded system is a system on chip, a microprocessor, a microcontroller, a GPU, whatever it is. It was designed by a hardware engineer so that you could compute something in it. The only thing that the computers can do is to count and add. There's nothing else. They do counting and adding. They just create multiplying and division or more complex operations out of it. So they can count and calculate. But however, in the end, although all of them does computation, their job is to compute, usually embedded systems are designed for a specific purpose only. So they are specialized. So we make architectural designs to specialize them. And this specialization comes with strengths and weaknesses, guys. And actually, these dimensions are about those strengths and weaknesses. If you're trying to do something high processing, like real-time video processing, well, you have to do computation a lot, but you will spend a lot of energy. But this is both a strength and a weakness. So your specific purpose as an embedded system will designate your strengths and weaknesses. And actually, the characteristics of embedded systems for deep learning regarding these strengths and weaknesses are quite clear, and we're going to talk about those. And we're going to introduce some important attributes that define the strength of our embedded deep learning systems and how they affect operation and why they are important. And in the following slides, we'll use these titles to compare different embedded solutions. We are going to first cover these computational attributes. After we understand them, we will come to the hardware platforms, CPUs, GPUs, TPUs, FPGAs, why one is better than the other if it is. In order to understand the strengths and weaknesses relatively among these hardware platforms, do I need a GPU? Do I need an FPGA? To answer for these questions, you have to understand these computational attributes first. Why? What is computational power? What is power efficiency? Etc. Okay, we start with computational power because it's the main title. It's also called the processing power. If you have an embedded system, what you basically do is you calculate. This is the most basic fundamental attribute. It shows the raw computational power of an embedded system. How many operations can you do? Because in the end, you are doing computation, and computation boils down to operations in your system. You make operations. Addition operation, multiplication operation, division operation, floating point operation, or integer operation. Doesn't matter. In the end, operations. And if you remember your microcontroller or microprocessor courses, all operations are actually constructed by so-called instructions, because instructions are the micro operations that the hardware do, whether it's a CPU or another type of architecture like GPU. So to understand it, for mostly CPUs, we use instructions per second. How many instructions can you do in a second? Or since instructions can vary from architecture to architecture, like for a CPU, it's an instruction set of assembly instructions, but for a GPU, it is kernel functions, which is something different we are going to talk about in the systems engineering videos. In those cases, we do something more common, operations per second, to measure this property. But even operations per second is not specific enough. Because specific to some applications, your operations can be integer operations or floating point operations. In those cases, if you're comparing a system which uses floating points, imagine you're trying to implement LXNet without quantization. In that case, your weights, your biases, your actuation functions are all floating point, as we've discussed in the previous week's slides. In those cases, you'll make a floating point analysis, and you're trying to understand in which embedded system it is working faster, with more accuracy. You want to understand the computational power, because all you care is the best accuracy. So you don't do any quantization. In that case, you'll be searching for a floating point operations per second, which is also abbreviated as flops. And it's mainly used because GPUs use flops, floating points. That's why when you're comparing GPUs, it's usually the flops you compare. How many billions of flops you do, kind of billions of floating point operations in a second you do. So flops is also used to indicate how many floating point operations of an embedded system is capable of performing each second. But this is specific. It might be for another type of comparison. It could be integer operations, IOPS, kind of. Okay. So let's understand these OPS in more detail, guys. I told you, operations in an embedded system may vary in type. CPU, GPU, FPGA, we'll talk about them. Well, an operation may indicate addition, multiplication, division, or even jump, depending on your level of optimization of your code. For different systems, they will take different clock cycles. I mean, for a CPU, depending on the clock frequency, like if you're running in 300 megahertz, whatever, gigahertz, 3 gigahertz, it will depend on the clock cycle. But not all operations take a single clock cycle. Or an addition take a single clock cycle if it is an integer addition, but if it's a floating point addition, it might take 4 cycles. For example, we have covered these. You remember I've told you a table in the previous week's slides showing the clock cycle count for each operation, floating point or integer, for an ARM microprocessor, for example, for a CPU. So in general, to calculate OPS in any context, whether it's flops or fixed point OPS or integer OPS, IOPS, we use the simple formula. Operations per second is the number of cores. Cores is the number of operating devices. So if it's a CPU, how many cores you have. If it's a GPU, how many GPU cores you have. Or if it's an FPGA, it has a different way of calculating it. So the number of cores, because they will do them in parallel. So cycles per second is your average cycle per second. This is the speed of the device. I say average, but it's usually fixed. For some systems it might change. But so what is your speed? If it's 3 megahertz, then in a single second you do 3 gigahertz, 3 billion cycles in a second. And finally, is operations per cycle. How many operations you do per cycle? It's usually a number lower than 1 because the fastest operation can be 1 cycle, but usually operations take 10 cycles. So this value is an average value because some operations you do, addition operation, will be taking 1 cycle. So it's average OPS per cycle depending on your design and architecture. So when you multiply these numbers, you get the OPS. And as I say, OPS per cycle may vary among operations, so we sometimes take the average value. This is how you simply calculate it. And actually, people will be giving you OPS or flops or GFlops, gigaflops. This is how they calculate it, and they make so many assumptions because getting this value, very strictly is quite impossible. You get an average which will give you an idea about the relative performance of the device.